now we should be good. Okay, doke. So the last time we met, at the very end, it was pointed out that I had this order swapped when we were talking about average types. That I had stated that if you look at the decreasing in tuples, that is going to be in d tensor d n times, whereas in fact it should be increasing in tuples. And then that sort of throws a wrench in our proof that if you realize inductively a average type, then it realizes the EM type of a given sequence. Now, let me just draw a picture so we have an intuitive picture of how this works. And then we'll see that, in fact, it was switched so that it realizes the EM type somehow with the variables in the opposite order, which is not a big deal. I mean, it's still an indiscernible sequence that realizes the EM type in the opposite direction, but this is how it works. So let's just think about it for a second. So let's consider the case that we're working in the rational numbers considered as a dense linear order. Okay, now sitting inside of, let's say that the rational numbers, like the picture I've drawn, let's say it's the monster model, and sitting inside, we're going to have the rational numbers here. So in some saturated elementary extension, we have a huge dense linear order, but sitting inside is the rational numbers. Okay, so we have some picture like this, and let's take our indiscernible sequence to be the natural numbers. So here we've got AI, I less than omega is our given sequence, and AI is just I. Okay, so now let's assume that we are given also D, which is non-principal, and an ultrafilter on omega. So let's suppose we choose B0 to realize the average type of D over the rational numbers. So where does that live? Where is it in this picture? So we'll draw it in red. What does, if I pick a rational number, then for all but finitely many of the natural numbers, I mean, all but finitely many of the natural numbers are greater than that rational number, right? So if I take a particular rational number, then eventually, like an n segment of the natural numbers will be bigger than it. So that means that the formula x is bigger than q will be in our type for every rational number. So a realization B0 should be like out here. And let me draw it a bit farther up because we're going to need space. So it'll be out here. It'll be bigger than every rational number, right? Now let's choose B1 to realize the average type of D over Q and this new element B0. So here's the observation to make. Every rational number, or sorry, every natural number sufficiently big enough will be between a given, okay, so let me say it this way. Suppose I hand you a rational number Q. Then for all but finitely many of the natural numbers, those natural numbers are between Q and B0, right? Like if I pick one of these blue points that I've drawn in my indiscernible sequence, they're less than B0, and they're bigger than the number I've picked for all but finitely many. So if I realize B1 will be here. And B2 will be here. Smaller than B1, bigger than every rational. So the sequence that I'm generating goes this way. But the sequence I started with went this way. And so, in fact, the order switched. So if you want to realize the EM type, you have to do it in the opposite order of the variables. And this isn't a big deal. It just means that you index it in the opposite direction. But okay, that's why there was this problem with the order in which things went. Okay, so the proof is correct modulo the change in direction. And then, okay, that's not a big deal. So like I said, I've posted the notes, and in the notes this is given in the correct order, correct proof. So if it's not clear how to make the modifications, then you can look at those notes, which are posted under the week 1 section of the CCLE page. But okay, I just wanted to point out that that's a confusing thing that happened last time, or 2 times ago. All right, so actually last time what we proved.
Like, Nick, just a quick question. So
yes,
in the second type, the average with the B0.
Yeah.
So for example, like the formula which says X is bigger than B0 is not in this type, right? Because
that's right. So my claim is like so for this,
yes.
Notice that suppose that we fix a rational number Q.
I mean,
then
you are allowed to take B0 as a parameter here.
Yeah, that's right. B0 is a parameter here. And so in this type, we notice that the I in omega such that Q is less than X is less than I is less than B0 is in D, because that's all but finitely many.
Yes.
Okay, so what that means is, in particular, the formula that says Q is less than X is less than B0 is in this type. But that's true for every Q. So because that's true for every Q, what that means is that B1 has to be smaller than B0, but bigger than every rational number. So it lives exactly where we drew it. Does that make sense?
Yes. So any realization of this type should be strictly less than B0.
That's right. Because the natural numbers themselves, all of the natural numbers are strictly less than B0. So a realization of the average type will also be.
Yes.
Okay, cool.
Thanks.
Very good. All right. So what did we do last time? Last time we proved that, well, we defined phi has the order property, which we'll abbreviate to OP, if there exist AI, BI, I less than omega, such that phi AI bj holds if and only if I is less than or equal to j. And as we mentioned, the less than or equal to doesn't matter. You could make it strict and it would still be the order property. And then we said that T is stable if no formula has the order property modulo T. And then we proved the following equivalence.
I have a question about this definition. Are we allowed parameters in the formula?
So it doesn't actually matter. So it's a great question. So suppose you have some formula, which is like phi x y, and then you have some additional tuple of parameters c. So let's suppose this has the order property via ai bi I less than omega. Then, for example, what I can do is I can define b prime I to be the tuple bi together with c. So now it's clear that the formula phi x y z has no parameters, and you have phi ai b prime j if and only if I is less than or equal to j. So if you have parameters, then you can sort of push them into the witnessing tuples. And if you do that, then you can assume that the formula doesn't have parameters. So the question of parameters sometimes doesn't make a big difference here. It's a good question though, because I'll use this fact all the time. If something with parameters has the order property, then something without also does. Okay, so good point. Okay, so the theorem that we had last time was just that the following are equivalent. Okay, that's essentially legible. Let me write it properly. The following are equivalent. One is that T is stable. And two is that every indiscernible sequence is an indiscernible set. Okay, now let's remember the difference. So indiscernible sequence says if I take two increasing intuples of indices, then the things that they index have the same type. Now, indiscernible set says that the order doesn't matter on the indices. So if I take two intuples of distinct elements from the sequence, maybe scrambled up in different order, then the things that they index have the same type. So indiscernible sets don't distinguish between the order on the index set, indiscernible sequences do. And so you might think, okay, if the theory can't tell, if the theory has no hint of order, then maybe it can't tell the difference between the two. And that's exactly what the proof did. So let's briefly recall how the proof went. So one direction is easy. If you have not one, then you get not two, because you can take the witnessing tuples in the order property to be indiscernible. So you start with some tuple, AI, BI, and you make that indiscernible using this theorem that we've proved twice. That if you have a sequence, you can find an indiscernible sequence that realizes the EM type. Now the EM type will say, if I take this index and then something later, then phi is true when I take the A coordinate and the B coordinate. But it'll say that if I take something late and then I take something earlier, then phi will be false when I take the A coordinate from the late guy and the B coordinate from the early one. And that means that the order matters. So I get an indiscernible sequence, which is not an indiscernible set. So that's very easy. From a witness to the order property, you can construct an indiscernible sequence, which is not an indiscernible set. The other direction was more tricky. And for this one, what did we do? So this is not two implies not one. What we did was we said, okay, so suppose I, which is AI, I in Q, by compactness, we could assume that our witnessing indiscernible sequence, which is not an indiscernible set, is indexed by the rational numbers. So you find some I in Q such that without loss of generality, for some phi x0 through x in minus 1, you have phi of a0 through a in minus 1 and not phi a I0, I think we called it J0, it doesn't matter, I in minus 1, for some I0 through I in minus 1, which actually just re-enumerate and through n minus 1. So I find two ways of listing 0 through n minus 1. One of them is the normal way. 0 goes to 0, 1 goes to 1, 2 goes to 2. It's like the identity permutation. And then I have some other way of scrambling it up, putting it in different order, where the truth value becomes false. And this you can do because you're working with an indiscernible sequence. So even though I start with two random intuples, I know that I can sort of slide them, preserving the orders, so that they have the same, so that they're two ways of ordering the same set. And without loss of generality, I can assume it's 0 through n minus 1. And then we know that there's a permutation sigma in Sn such that sigma of, let's say it this way, let's just say it this way. Sigma of 0 equal, sigma of j equals I sub j for all j less than n. Okay, so I can, since I have two ways of scrambling, there's a permutation that does that, and I can write this permutation as a composition of transpositions which swap consecutive elements. So write sigma as composition of transpositions that swap consecutive elements. Then there's a first swap that changes the truth value. So we had our sequence indexed by Q. So we have like A, Q, Q, and Q, which is our sequence. And we restricted attention to, a certain collection of elements. So we've got like 0 through n-1. So here's 0, here's 1, here's n-1. And what we did was we found that, okay, if I swap just 2 of these guys, which are right next to each other, then the truth value goes from, let's say, true to false. So it goes from true to false. And that means that you find the order property, because if you freeze all the other things as parameters, so let's just pretend like these guys are parameters. Then whenever we take 2 things inside here by indiscernibility, these pink things, we know that if they're in one order, the formula is true, and if they're in the other order, the formula is false. Now, why is it important that they're in consecutive, that they live between 2 consecutive numbers? Well, because if I have them situated inside this interval between, I don't know, let's call this k and k plus 1. If they're situated inside this interval between k and k plus 1, then their ordering relative to all of the other terms in the sequence is the same. And that means that by indiscernibility, I know that when they're in the correct order, the formula is true. When they're in the swapped order, the formula is false, by indiscernibility. So that's why it's actually kind of important. I think I didn't really appreciate this point until I looked over at the proof to teach it to you, which is that it's not just the fact that you write the permutation as a product of transpositions, but in fact you write it as transpositions where the elements are consecutive. And that consecutivity means that the order relations between the indices will be preserved. And so by indiscernibility, you know that for any 2 that you pick inside this interval, one way it'll be true, one way it'll be false. And then we use the fact that the sequence was indexed by the rational numbers. So there are infinitely many tuples living inside this interval. In one direction it's true, and the other direction it's false. That's what you need for the order property. So that was the proof in a very sort of schematic way. And the reason I wanted to do this sort of overview is that we're going to do this again, almost the same proof, to prove a sort of fundamental dichotomy theorem of Shelah. So I want to move toward that direction now. And this theorem doesn't have a name, but I'm just going to call it Shelah's first dichotomy theorem, and maybe that'll stick someday. So let's write that. So Shelah's first dichotomy theorem. So in order to get to the statement, we need some definitions, which are going to generalize the definition of the order property in various ways. So recall, we had 2 examples last time of theories with the order property. So the first one was DLO, the theory of dense linear order. So this is like the rationals with less than. And here it was very easy. The formula that we looked at was just x is less than or equal to y. And you can take your sequence to be any increasing sequence of rational numbers. AI equals BI equals I was the example we gave, and that worked great. So notice here, it's not just that you have the order property, but in fact you have an interpretable linear order. Here there's like a linear order in the structure that orders a collection of tuples, and it's definable. It's like very clear on the entire model. You have a linear order. So this is like a real order. Now, in the other case that we looked at, it looked very different. We had the random graph. So this was like GR. And here, the way we found the order property was we looked at these half graphs. So we had a collection of tuples. Where the vertices were connected like this. And on this sequence of pairs, we were able to find the order property. But the sort of space of vertices on which the formula, let's say R, X, Y, witness the order property is not definable. And it's very easy to check just using the axioms of the random graph that in fact there is no interpretable linear order, no interpretable partial order anywhere inside the structure. So what Shelah proves is that in some sense, these are the only two examples. And every time you have the order property, it either comes from something very rigid in the sense that you have an interpretable partial order around, or it comes from something very random in the sense that it looks like you have a random bipartite graph or a random graph around. And so even though these two situations look like very extreme, in fact, they're representative of the full range. You always have to have something very random or something very structured in the case that you have the order property. So that's why it's a dichotomy theorem. Of course, it's not truly a dichotomy in the sense that everything has to be in one or the two. Because, for example, to give a trivial example, you can just take a structure which has a linear order and a random graph in it. And then it will have both. More naturally, if you look at like piano arithmetic, you can check that the divisibility relation satisfies something very random, which we'll describe in a moment, but it also has the linear order on the natural numbers. So it sort of packages both. So you have lots of things like this, but everything will contain at least one of these two extremal configurations. So I want to define what are these extremal configurations more precisely now. So here's the definition. Let's start with the independence property. So many of you have probably heard of the theories without the independence property, the NIP theories. They're very important. So let's say what it means. So formula phi xy has the independence property, which we write IP, if for all n less than omega, well, it doesn't matter. For all n, there are a0 through an minus 1 such that for all w, let me write this on a new line. For all w, which are subsets of 0 through n minus 1, we have that if I look at the formula that says the conjunction over all I less than n, phi x ai, if I is in w, that's consistent, that's true. So what does this mean? So first comment is here in this exponent. How do I understand what that means? Well, in general, if I write phi and then I put a true statement in the exponent, then that means phi. And if I have phi and I put a false statement in the exponent, that means not phi. Okay, so this is just notation. So what does this configuration say? It says I have n elements which are indexed by the numbers up to n minus 1. So a0, a1, dot, 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 an minus 1. And suppose I just make a decision about which ones I want to connect to via phi. So let's say I want to connect to this one, I want to connect to this one, and I want to not connect to this one. I want to not connect to this one, and then I want to connect to this one and this one. So what the configuration says is that I can find some x, which indeed connects via phi to these, and does not connect to these. So I'm imagining that these green things here are my W. Whenever I see an index which is in W, then I want phi to hold on X and that parameter. And whenever I see something that's outside of W, I want phi not to hold. And is it possible to find an X such that I have this configuration where I say yes to the things in W and I say no to the things not in W? And the independence property says that I can always do that. Okay, is that clear? So this is some kind of strange thing, but we'll notice that the random graph has exactly this property. So suppose I take in vertices inside the random graph. So this is like V0, V1, V2, all the way through Vn minus 1. Let's recall what the random graph axiom said. They said that if I had two disjoint sets of vertices, that I could find a vertex that connected to the things in one of the sets and it didn't connect to anything in the other. That's exactly what the axiom said. So of course, if I take some subset of these vertices, I can find some other vertex, let's call it W, or maybe not W since W is used as this index set. Let's call it U, which connects to these vertices and does not connect to any other vertices. And as a consequence, that means that Rxy in the random graph has the independence property. Okay. Now let's give one more example, which is I think interesting and not totally obvious, which is that of the divisibility relation on.
So Nick,
yeah.
Just to be clear, in the formula you give, there exists an X. You need to add the conjunction of the negations when you are outside W, or this is what
no, that's included. So here, what did I write? The exponent here is if I is in W. And I clarified it that like if I have a true statement in the exponent, that means yes, the formula is true as stated. So that means that I have positive instance for all the i's that are in W. And then when the statement in the exponent is false, I have the negation. So
I see. So this is an exponent.
Yes, that's an exponent.
Yeah, okay.
Yeah, so just in case it's not clear to those of you that are not Dowd, like if W is like 0 and 2, living inside of the set 0, 1, 2, then the statement, there exists X and I less than 3, phi X AI, and then in the exponent, if I is in W, this is the same as the statement, there exists X such that phi X A0 and not phi X A1 and phi X A2, like that. Does that make sense? So this is just shorthand because it's convenient and we'll use it. Okay. Very good. Cool. So now let's look at the divisibility relation. So we have X less than Y in the natural numbers plus times means X divides Y, i.e. there exists some Z such that Z times X equals Y in Peano arithmetic. All right, so now suppose let P1 through let Pn through Pn minus 1 be the first n primes. Then, given any w contained in 0 through n minus 1, we let a, or let's call it b sub w, just be the product over all I in w of pi. So if I take a subset of the indices from 0 through n minus 1, I can take the product of just the primes that are indexed by the elements of that set and none of the others. Okay, then notice that we have pi divides bw if and only if I is in w. Because what are the primes that divide w or bw? It's just the ones that I included in my product, which are just the ones that are indexed by elements of w. And what that means is that bw satisfies this collection of formulas that say phi x ai if I is in w as I ranges over the numbers through n. So there is a witness. And so that means that x divides y has IP. So here again, you have something that looks kind of random, even though you maybe don't think of piano arithmetic as the most random kind of thing. It's not a for say limit of anything. All right, so this is one of the properties. And this one says, in some vague sense, that your theory looks like the random graph. Now, let's consider a different property called the strict order property. So phi x, y has the strict order property, which is abbreviated SOP, if there exists some sequence AI, I less than omega, such that you have, there exists some x, so that you have not phi a k and phi x al, if and only if k is strictly less than l. All right, now here's the official definition, but we're logicians, right? So we know how to negate things. What is the negation of this biconditional? Like what happens if I add negations on both sides? Of course, that still preserves the biconditional. So if I negate both sides, what does this say? This says for all x, we have to do De Morgan's law, right? So now this is phi x ak or not phi x al if and only if k is greater than or equal to l. I believe that's the negation on both sides. And then we remember the definition of the material conditional. A implies B is the same thing as not A or B. We're really doing propositional logic now. And so this happens if and only if what? This happens if and only if for all x phi a l implies phi x a k. Okay, so what does this say? This says that I have some formula which defines sets. And as I move smaller in my indices, I'm getting bigger sets. So what does it mean for phi x al to imply phi x ak? It means that the definable set, the set defined by phi x al is strictly contained, is contained in the set defined by phi x ak. So as k increases, I have this like growing concentric circles. So I imagine that I have something like phi x A0. And then I'm going to have some bigger thing, which is phi x A1. And I'm going to have phi x A0 strictly contained inside. And I'm going to have this bigger one, which is like phi x A2. And so this defines a kind of partial order. I can look at the partial order, which says that, so we get a partial order with infinite chains defined by, let's say, z is less than or equal to y. Well, the order doesn't matter. If and only if, let's say, for every x, if phi x y holds, then phi x z holds. Okay. Now, this is always a partial order, just always, always, always. But normally, it's not a very interesting partial order. The chains will be finite. But in the case that you have the strict order property, the chains are infinite. You can find an infinite sequence like this. And an example to have in mind is in DLO. You can look at the formula. Let's say x is less than y. And now, as you look at the sets that this defines, sort of in DLO, if I pick a bunch of elements, so like let's say here's A0, here's A1, here's A2, here's A3, what are the sets that are defined by x less than AI? Well, okay, if I look at the set defined by this formula, less than A0, I get this interval. Now, if I look at the set that is defined by x less than A1, I get this interval. And if I look at the set defined x less than A2, I get this interval. So I have strict containment between them. And anytime I have infinite chains of strict containment, instances of one definable set and another, I get the strict order property because I have a partial order with infinite chains. Okay, is this clear? So the theorem now, Shelah's theorem, which I hope we can prove, is okay, phi has the order property, or let me say it this way, T has the order property. If and only if sorry, T is not stable. I didn't say what it means for, okay, T is not stable. It means the same thing. If and only if some formula has the IP or SOP. So if you have the order property, if some formula has the order property, then some formula has to have one of these extreme forms. Either you have to have something very rigid, like a partial order, or you have to have something very random, like the configuration described in the independence property. Okay, now one direction I will leave to you. So exercise, show if a formula has IP or SOP, then it has OP. So these are in fact stronger forms. Now, why? Let me give a hint. I mean, for the order property, what did you have to say? You had to say that if you have a sequence that's of a certain length, then it's okay to say yes to an initial segment and no to an end segment. Now, the independence property says no matter which subset you take, you can say yes to the subset and no to the complement. So of course you can find the order property. And then for the strict order property, it's even easier. So this is not a difficult thing. And then it's good to just make sure you understand the definitions to be able to prove this. So the other direction is going to be more complicated. And I think we have just enough time to do it. So let me get my notes. I don't want to screw it up. All right. So so other direction. So suppose phi xy has the order property. So by our indiscernibility results, there is a sequence AI, BI, I now in Q, which is indiscernible. And satisfies phi A Q B Q prime, if and only if Q is less than or equal to Q prime. This is just a compactness argument, and using and using the result that we had before. So we know that you're going to have some collection of tuples that witness to the order property. You can make them indiscernible by using our results about EM types, and then you can make them indexed by Q by compactness. So this is a simple thing using the arguments that we've described before. All right. Now, we know by, okay, let's assume phi does not have IP. So we're going to just assume that that IP is not present, and then we need to find SOP. So the assumption that we do not have IP means that there is some n less than omega and W contained in the set 0 through n minus 1 such that the conjunction, well, let's say it this way, it's not satisfied that there exists an X such that for all I less than n, phi X AI is true if and only if I is in W. Okay, so if we could do that for all n and for all W, then we would have the order, the independence property. We know that it's not, so we can find some n and some W that witness that not every pattern of consistency is consistent. Not every sequence of yeses and nos will give us a correct answer. So let's look at the picture first. So we've got, we've got our indiscernible sequence, and here we've got, say, 0, 1, 2, 3. 0, 1, 2, 3. I'm going to double it. Now, what we know is if I say yes, yes, no, no, this is consistent. Why? Well, because I started with the assumption that I had the order property. So if I say, I connect to the small things and I disconnect to the big things, that's okay. That's consistent because the order property says that I can do that. Now, on the other hand, I'm going to have some set which says that, like, if I say yes here and yes here, but no here and no here, for example, let's say maybe this is W, then this is not consistent. And so I'm going to do exactly what I did before. I know that I can get from the offending inconsistent configuration to the correct consistent configuration by a sequence of transpositions. So for example, I could make this swap, and then I can make this swap, and now I would look like the first picture. Does everyone see that? Like if I first do this, and then I do this, then I end up with the first. And so there has to be some binary swap of consecutive transpositions of consecutive elements that switch me from something inconsistent to something consistent. So I'm gonna give that explicitly, but that's the basic idea. All right, so what we'll do is we will let the cardinality of W be in 0, which we know is less than n. It's a proper subset, it has to be. You can certainly say no to all of them and you can say yes to all of them. Then there is an alpha less than omega such that we can define WL for L less than or equal to alpha such that what? Well, we're going to have a few conditions. So the first condition is that W0 is W, the one we started with, and W alpha will consist of n minus n0, n minus n0 plus 1, dot, 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 n minus 1. So it's an n segment. So I think I said this backwards. I think what I meant to say is that you can say, sorry, the order property gives you the opposite. It should have looked like no, no, yes, yes. Sorry. Two is for every L, the size of WL is equal to n0, so the size doesn't change. And 3 is there, for every L, there is KL such that WL plus 1 is going to be WL, take away KL, union KL plus 1. So I'm just swapping these two consecutive elements, and I'm favoring the greater one. And this you can do. So we are assuming, recall that we have, it's not satisfied that x I less than n phi x ai I in W0 is right. But, oh, sorry, let me also say, oh, right, no, sorry. So remember that we have W alpha is the in segment. And because we assumed that it had the order property, we have the exist x I less than n phi x ai I in W alpha is true. It is consistent because this is what the order property says. I can work with the in segment and say no to the initial segment, then I'm good. So so there's a first L star such that we have not there exists x and I less than n phi x ai I in W L star, and there exists x conjunction I less than n phi x ai I in W L star plus 1. The truth value has to change at some place. So now let's just conclude the argument. So what we'll do is we will let C x y be the conjunction over all I less than n I not equal to I think it's K L. I want to make sure I get this right. Yeah, let's say it's not equal to KL and it's not equal to KL plus 1. Okay, good. So then I'm going to have phi x ai, and then I'll just add phi x y here. So I omit the two that I swap, and then I just add an extra instance of the formula. And the way I've written this, I've suppressed the parameters in C. Okay. So let's draw the picture here. I had my collection, and I had some situation where, for example, if I said yes, yes, no, yes, no, this was inconsistent. But if I swapped these two, then it became consistent. Or let's say not those two. Let's say the other. Let's say if I swap these two, then I know it became consistent, right? So now what I'll do is I will freeze this and these two as parameters. These are just frozen into C as parameters. And then what I have is now for all q less than q prime in the interval kl plus 1, we have that there is cx a q sorry, oops, oh, whoa, I don't know what just happened. How do you get rid of this thing? Oh, there we go. Okay, that's a strange thing. So we have not this one and c x a q prime if and only if q is, sorry, let me say it this way. For all q prime inside this interval, if and only if q is less than or equal to q prime, strictly less. And that means that you have the strict order property. Okay, so this is very technical to write it down precisely, but the idea I think is very clear, which is that you say there is an x which satisfies something when I have the configuration in one direction. If I make a single binary swap of consecutive elements, then the truth value changes. Then there's no longer an element. So I know that I can freeze all of the things except for that pair, think of them as parameters, and then on this indiscernible sequence indexed by the rational numbers in between, I have exactly the strict order property. When they're in the right order, there is an x which says yes to one and no to the other. And if I switch them, then there's not. And that's what the strict order property says. Now, the strict order property is equivalent to saying that you have an interpretable partial order with infinite chains. So what this really says is that if you have a formula with the order property, then either it comes from something very random or it comes from something that looks like a partial order. And that's a kind of dichotomy. Okay, so the reason this is called the first dichotomy theorem is because there's a second one, which has to do with trees. And that's what we're going to be building toward next. So the main theorem, probably at the beginning of next week, but maybe by Friday if we're lucky, will be the second dichotomy theorem, which is sort of the same theorem, but now on trees instead of sequences. And so that's really sort of the direction we're headed. And then we're finally going to be doing model-theoretic tree properties. So the first bit was sort of like, this is what you can do with indiscernible sequences. Now we're going to be done with indiscernible sequences. And next time we'll pick up with indiscernible structures, generalized indiscernibles. So that's the direction we're headed. All right, so I think that's all I wanted to say today. I went a bit over, I apologize. Are there any questions? No? All right, well, I will stop recording.